Alright, so we're going to talk about some piecewise functions. Okay? First piecewise function I want to talk about is that one. Okay, so this is kind of, we're going to see some questions the web assignment asks you to do piecewise functions, but their graphing tools and techniques are kind of limited. So we're going to, for the most part, when I give you piecewise stuff, see this on Monday, I'm going to give you a handout to do your homework in. But we'll practice this today. Hopefully it's nothing that's extremely confusing. You already know how to graph the functions that we're going to deal with. And if you don't specifically know how to graph that type of function, so if I give you like an exponential function or something like that, you can at least still plug in and create a t-chart like x and y's and plug in and evaluate and see what you get back for y. And that's really what we do a lot in regards to the piecewise functions early on, is that evaluating process, but hopefully we can do it in kind of in a quick manner, kind of maybe going off of knowing that, with x squared, some key points are 0, 0, 1, 1, 2, 4, so forth, and then you get those points and you can develop that graph pretty quickly. But it's more of a notation understanding, I think, right now, and a procedural thing for people that they get hung up on and have troubles with in regards to piecewise functions. Okay? The notation there says f of x is equal to, and it's got that curly brace, x squared, but it's only going to be equal to x squared if x is less than or equal to 1. Okay? So what that's telling you, remember, f of x is a rule to provide y values, right? It's a rule to provide you y values, okay? When you know a specific x value. When I choose x values to plug in, I get y values back. So if I didn't have any restriction, I just had f of x equals x squared, you are allowed to choose any values out of that domain, right? Okay, the domain for x squared is all real numbers. Right now what we're saying is that you can't do that anymore. Right now with this function x squared, if x is less than or equal to 1, the values you're allowed to use from the domain are 1 and things to the left of it. Okay? And then that's going to incorporate y values that kind of play off of what that x value was. Okay? And it's really, it's a notation that I think people don't like. It scares them. But what it really means is f of x equals x squared if x is less than or equal to 1. So it means you're going to get y values that follow this rule if you have x values that are less than or equal to 1. And then you have another rule that says f of x equals 2x plus 1. Okay? If x is greater than 1. So your y values are going to be developed, okay, by taking x values that are bigger than 1, plugging it in there, okay? And then we graph those two things on the same graph. Okay? So it's really just graphing multiple functions on the same graph. But what happens is that we don't really like to write this out twice. Okay? So that logic or that concept gets converted into that notation. Okay? And inside that bracket, you can have as many functions as you want. Okay? It can be 2, it can be 3. I think there's a couple questions on WebAssign that might have 4 or 5. But a lot of them are kind of simplistic functions. You might have 2 that are, you have to do a lot of plugging values in and stuff like that, but then you'll have 3 or 4 that are maybe constant functions, kind of easy to deal with. What we need to understand though is that they're telling us this thing's a function. Okay? So because it's a function, it always has to pass what? Vertical line test. Okay? So when we're done, we should be able to pass the vertical line test through and recognize that at most you intersect your curve 1 time, right? Okay? If I intersect my curve 0 times, is it still past the vertical line test? Yes. Okay? The vertical line test is defined to fail only when you intersect more than once. So intersecting once or 0 times is fine. Okay? So this is kind of how we go about doing this. The first thing is that those rules over there, call them restrictions. Okay? Restrictions on the domain or maybe conditions on the domain. Those are kind of your starting points. Okay? And in this case, it's the value of 1. And we're going to use that value of 1 in both equations, x squared and 2x plus 1, But because one's equal to and one's greater than, we're going to graphically kind of demonstrate that solution, that value that we evaluate a little bit differently. So let's just start with that top one. It says x squared, but you're only going to say x squared. You're only going to evaluate x squared if x is less than or equal to 1. So let's start at 1. If x is 1, what would you get back? 1. Okay? So I got the point 1, 1. I'll plot that. Okay? Now there's a vast amount of techniques that you can use to graph things. Okay? For instance, lines. I can do an XY chart. I can go y-intercept and slope, that kind of stuff. So you got multiple techniques to graph lines. There's multiple techniques to graph other functions. I like to use a collection of those to try to maintain efficiency. Okay? And I don't like to say, every one of these I'm going to create a big T-chart with X's and Y's and evaluate 200 points for each one of them. That's going to be very time consuming. So use your knowledge about how to graph functions efficiently. And it's ultimately up to you. The way you do it might be different than the way your neighbor does it. Does that make sense? Okay. But our goal is to get that final graph. Okay. So now if x is less than 1, okay, we're now looking at just basically those x values there. We don't care about what happens to the right of 1 for x squared. Okay. So we're going to start plugging in x values that look like 0 and -1 and -2, stuff like that. So I plug 0 in and I square it, I get a 0, right? Plug -1 in and square it, I get 1. -2 squared, -2 squared is 4. -3 squared is 9. And what I'm using there is just the knowledge of x squared in the maybe 5 or 6 ordered pairs that we've memorized maybe from yesterday that always go with x squared, right? Okay, that parent function. So we graph those. Now, when we have a graph here like this, we're going to connect it. Smooth curve. Okay. You guys have all seen, like in coloring, little children's coloring books, they have like, they take a picture and then they white out some of the lines and they put dots and numbers on those and you got to connect them, right? And every kid like goes with a straight line from one dot to the next dot to the next dot, right? And it looks really choppy when you're done, okay? Don't do that. You're going to see this all the time. I see people do this. Okay? That's not a parabola, right? That's not x squared, okay? The segments there, that segment that I just drew there is not representative of x squared between those two x values. Okay, so make sure you're making a smooth curve, and that goes for everything throughout the year. Smooth curves. Now I'm going to put an arrow on the end of that because what this said here. X is less than or equal to 1. So does that tell me I can go use an x value of -100? I can use x value of -1 million, -1 trillion, okay, whatever. So I'm getting x values that are all the way over here. And obviously I don't have those graphed, but that arrow tells me that I can use those, and those will show up. Okay. If I didn't put an arrow on there, you're telling people, so if I did maybe that, you're telling people that this graph actually stopped at an x value of -3. Does that make sense? Okay. And we're seeing that it's not stopping, so we need that arrow. Alright, so that's the first rule. Okay, once you get that first rule knocked out, you go to the next one. Okay? So you go 2x plus 1 if x is greater than 1. Okay? Now here's the procedure, the technique with piecewise functions. Okay? We know that 1 belonged to this rule, right? If x was 1, it belonged to this rule. Okay? Here we want to choose a number like 1.000000000000001. Right? All those zeros and a 1 on the other. Well, if I evaluate that, if I take 2 times that number, I get something really close to 2.0000000000002, right? And if I add 1 to that, don't I get 3.0000000000002? So I started with a number just to the right of 1. And I get a number just to the right of 3. Does that make sense? Okay. So why can't I just evaluate at 1 and get 3? And then realize that idea of using that number that's very close to 1 and getting the number back that's very close to 3. Plot 1, 3. But instead of coloring it in, I leave it open. And that open dot then tells me that I evaluate at 1.0, a bunch of zeros and a 1, and I should get back something like 3, a decimal, a bunch of zeros and a 1. Does that kind of make sense to everybody? Okay? So the logic or the math idea behind it is that you're not really using 1 to evaluate here. You're using something very minute in regards to the difference between 1 and the number that you're going to evaluate at. And that very, very small amount is negligible. So let's just go ahead and evaluate at 1, see what we get, and then the open dot kind of wraps all that logic in there and saying we're really not getting 1, 3 back. We're getting something to the right of 1 and to the right of 3 back. Is that okay with everybody? I'll make sure we understand. That's a huge issue that people struggle with. And what people want to do a lot of times is they say x has got to be greater than 1. So what's the first number you normally think about? If I was to ask like an 8th grader or a 7th grader, what's the first number bigger than 1? They usually say what? 2. Okay? But we know that's not the case. There's an infinite number of values between 1 and 2 that we just skipped over. Okay? So we have to use that 1. Does that make sense? Okay? A lot of times on tests and quizzes, I will see the first point people will graph will be that one. And they'll skip all this information in between because they think the first number bigger than 1 is 2. Okay? The first integer bigger than 1 is 2, but that's not what we're looking at here. Okay? I'm talking about real numbers. So then from there, how many points do you need for a line? 2, right? Okay. So I'm going to use my slope. Okay, and I know that this thing is going greater than 1, and the slope is positive. So I need to graph this direction. Does that make sense? Okay. So I'm going to go up 2 over 1, up 2 over 1, up 2 over 1. Get enough points in there for me to graph my line. Okay. There are other techniques for graphing lines, right? Could you use y-intercepts? Could I graph the point 0, 1 right there, and then going up 2 over 1, up 2 over 1, and keep repeating that process? Okay. But if I did that, that y-intercept has an x value of what? What's the x value of that point right there? 0, right? This rule says you can't use x to be 0 here. So that's why maybe it's not a good idea in this situation to graph using y-intercepts. Okay? So we get that one out of there. That is your final graph. That is what we call a piecewise function. Notice it's in pieces, right? Okay? And notice it's a function. That's the key thing here. These are all called piecewise functions. So they should pass this thing. I should be able to take this vertical line. Passes, 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 passes. And there's an issue right there, right? Well, there may be an issue there. But because we put an open dot on the blue, that means that that blue segment, that blue ray, actually starts just to the right of that vertical line, and it really doesn't touch it. Does that make sense? Okay. But it does touch the red one, right? Okay. So when you're doing these and you're just checking to make sure you've done things correctly, remind yourself you got to pass the vertical line test. And 90% of the time when somebody gets these wrong, it's because they came to those 2 spots right there and they filled they filled both of them in, and it fails the vertical line test when you do that, and it violates the rules of being a function. Is it okay? Let's do another one. Let's go. F of x is equal to taking the last class, just keep trying to maintain what we did in the last class. 1/2 x squared square root of x. X is greater than or equal to 0, and let's say negative 5 when x is less less than negative 6. So here we've got 3 rules, right? Okay, and 3 restrictions off their domains. Just kind of giving you maybe an alternative way that you might see these, just so nobody's confused later. It's dependent on the author. The last one you saw, they used the word if, right? Okay. Some of them, that word gets taken out and they replace it with the word when. Some of them take the word out completely and they just put in a semicolon. That's the way I do it. You can also see stuff like this. They might write the, let's say, use a set notation in your intervals. They might use interval notation. Okay, so but you read them the same way. Just telling you the x values that you're allowed to use for those functions. So if I'm just going to focus on this one. I think that's the easiest one for people to read. If we say 1/2 x squared is our rule, but we're only going to use that for values between -4 and 0. So what I know is I first want to evaluate at -4. I then also want to, when I'm done, make sure that I've evaluated at 0. When you have a between statement, you want to make sure that you evaluate at the beginning and at the end. Okay? So if I evaluate at -4, I'm going to square that, I get 16. Take half that, I get 8. So at -4, I'm up at 8. Okay? Now because -4 was less than or equal to, I'm going to put a closed dot there. Okay? Now I'm going to evaluate at 0. I just want to show you something that people like to do and it creates issues. Evaluate at 0. If I evaluate at 0, I get 0 back, right? And people consistently, now I did that wrong, it's a less than sign, right? So what kind of dot do I use? Open. Okay? People consistently do this and they think that's the only places I have to evaluate at. Okay? Well, if your graph is nonlinear, okay, you need more than 2 points, right? So put a third point in there, put a fourth point if it's nonlinear so you get a good smooth curve. I'm going to try even number. I'm going to put one more in. I'll put an even number here because of that 1/2. So I go -2. That's between these two values, right? -2 is in that interval. So I try -2, square, I get 4. Take half of it, I get 2, right? So -2, 2 should be a point. And there's my curve for 1/2 x squared. Okay? Hopefully you can visualize what 1/2 x squared would normally look like if we use the entire domain. And now this is kind of just erasing everything outside of -4, everything to the left of -4, and everything to the right of 0. Okay? I have seen people kind of develop that technique before on their own. It says, I'm not even going to really worry about the restriction. I'm going to graph the entire thing. And once I have the entire thing done, I'm then going to go find the x values that they're interested in, and I'm going to erase everything else. Okay? All the other x values. So that's one way to kind of try and explain what I'm doing here. Some people will do this. Okay, so graph the whole thing, 1/2 x squared. They say, well, I'm only interested between -4 and 0. I'm only interested in the graph basically inside that block, right? So they go through and say, okay, I'm going to erase that, now erase that, and then the red curve that they're left with is what we were interested in. Does that make sense? I think that's maybe more tedious than what's needed. It's going to get your paper all messed up and messy looking with eraser marks and stuff like that, but it is a route to take if you want to. The next thing I want to do is look at the square root of x when x is greater than or equal to 0. Square root of x when x is greater than or equal to 0. So, again, I have to use the starting point of that interval. Okay? So starting point of that interval is 0, right? Can you take square root of 0? Yep. Because if I think about this, square root of 0, remember that's a symbol for the number that I multiply by itself 2 times to get me the radicand, the number underneath. Okay? And 0 will do that, right? 0 times 0 will give me that 0. So I can't take the square root of 0. So plugging 0 in here, I get 0 back, right? Okay. Now it's equality. So 0, 0 needs to be plotted, and it's an equality. Okay, so there was an open dot there, right? But in another rule, we find out that that open dot now got closed. Is that all right, everybody? Okay. And that's perfectly fine. That's okay to do. The next thing is to choose values that are easy to take the square root of. So I'm not going to choose like 3, because square root of 3 is kind of hard to figure out, right? 1.7 something. But it's not easy to graph. But a square root of 4 is easy to graph, right? 4 comma 2. 9, easy to graph. Okay, 9 comma 3. And now I've got my smooth curve for my square root function. Okay. The next thing I want to talk about then is the -5. Okay. The -5 is, you remember what this means. Remember what all these things tell us. And this one, I think this is one of those situations that it's simple, so simple that we make it hard. Remember all these things mean their individual function, right? So f of x equals this junk. I could separate those into 3 rules, and it would look like that, right? Well, we know f of x, the f of x values are essentially the same thing as your y values. So there I've got y equals -5. What kind of line is y equals -5? Horizontal. Through -5, right? Okay. But we're only going to be interested in the values of x that were less than -6. So what that means, when you have -6, you should have a y value of -5, right? When you have an x value of -7, you should have a y value of -5. When you have a y value of -10, you should have, an x value of -10, you should have a y value of -5, right? Okay. This -5 is constant for whatever x value you have that abides by that rule, okay, or by that condition. So it says x is less than -6. Again, this is a situation where you still have to use -6. That has to be one of the points that you plot. So I'm going to find x to be -6. So 3, 4, 5, 6, right there. Okay. And then the y value that's with that would be -5. So I'm going to find -5, 1, 2, 3, 4, 5. So my point is right there. But I'm going to make it an open point, an open dot, because that tells me that I can use -6.000000000001 and get a y value of -5 back. But I can't use -6 and get a y value of -5 back, right? Okay. -6 comma -5 is really a point that does not exist on that graph. Okay. But the best way of showing that the point right to the left of it, the immediate left of it, does exist is with that open dot. And now anything to the left of -6, like -7, is going to have a y value of -5. -8, -9, -10, all going to have y values of -5. So then we have that horizontal line. Okay. Now the idea is, remember this was a function, so the vertical line test has to work. So start over here, start tracing my vertical line through. Does it pass there? Where that open dot was?
No.
It does. The vertical line test says to pass vertical line test, any vertical line can intersect your curve at most being the limit, right? Can't go over that. At most 1. Okay? Or once. Okay? There's right one time. Okay? To pass the vertical line test, any vertical line can intersect your curve at most one time. Okay? And it might be a good idea, when I say any vertical line, we're really thinking about all vertical lines. Okay? So that's why we're passing that through and moving that from left to right. At most 1, okay, or at most once, means means you could have things that are below that, right? Well, below that are 0, correct? Doesn't really make sense to intersect -1 times or anything like that. So I could, if I pass the vertical line test, it's because my graph was intersected by a vertical line 1 time or 0 times. So if I'm right there, is this intersecting 0 times right here? Yeah, so it's passing. What about right there? Is it intersecting 0 times there? Yeah, so it's passing. So the logic that, it didn't intersect any of my curve here is the same as it didn't intersect any of my curve here. Okay? Because that opened out. How many times do you intersect there? Once. What about there? What about there? What about here? Once. Remember, it was open and we filled it in, right? Okay, so there really is only one point there. So we only intersect once there, and then the same thing throughout. Okay? When we want to test the vertical line test, you intersect at most 1 time. Okay?